Let's say you have a right circular cone and you have this is your height and this is your radius. And let's suppose for a moment that you have water that is coming into this cone at a particular rate. Well, we could say that there are three things that are changing as time is changing. As time is ticking, you could say that as the water level is rising, the volume is changing with respect to time. You could say that the radius of the level of the water is changing with respect to time. And you could also say that the height of the water is changing with respect to time. So what we want to do with this related rates is basically we want to figure out how fast one of these quantities is changing as the other two quantities are changing. So we may be interested in figuring out how fast is the volume of this cone changing at the very instant when the height of the water is 3, or at the time when the radius may be 2. So that's what we're going to talk about in this video. We're going to talk about how to find rates of change. Okay, just like we had certain steps that we needed to follow for optimization, we're going to also give you some steps to follow for related rates as well. Number 1, identify all given quantities and quantities to be determined. Each problem will give you something. They'll give you either a radius or a height or the rate at a certain time or whatnot. Make a sketch and label the quantities. Number 2, write an equation involving the variables whose rates of change either are given or are to be determined. Now, different than optimization, you do not need to write these in terms of one variable because step 3, you're going to use the chain rule to implicitly differentiate both sides of the equation with respect to time. So this is the key. You have to remember that each variable in the equation is dependent upon time. The radius is changing with respect to time. The height is changing with respect to time. The volume is changing with respect to time. So when you're taking the derivative, you're not taking the derivative with respect to r or h. You're taking it with respect to t. So you have to use implicit differentiation all the way across. Now, after completing step 3, and only after completing step 3, you will substitute into the resulting equation all known values for the variables and their rates of change, then solve for the required rate of change. Now, it's also important to understand here that if something is constant throughout the entire problem, then you don't need to assign a variable to it. A variable is just that. It's something that is changing. So anything in the problem that is changing, like height or radius or whatnot, that needs to be a variable. If it is static and it's the same, then you can use that number throughout the whole problem. Let's see how this works on a few sample problems. Okay, let's look at this first problem. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner. So here is the police car. Here is the other car. The police car is trying to chase this car. The police car is going south. The other car is going east. And it says here when the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determined with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, let's go through the process. What has been given to us? What has been given to us is, well, we know that 0.6 is going to be our y, because it says that the police car is 0.6 miles north, and it says that at that time the car is going to be a 0.8 east, so we know our x is going to be 0.8, and then our it says that the distance between them is increasing. So you got to pay attention to words like increasing because that means to make the rate positive. If it was decreasing, that would mean to make the rate negative. So we can say our dz dt, or let's interpret that, the change or difference in the z as time is changing is going to be positive 20. Now at that time, the police car is moving south, so dy dt is going to be negative 60, all right, because it's moving south. And what are we looking for in this problem? what is the speed of the car? So we're looking for dx dt. That's the question. So we're going to use our Pythagorean theorem and just basically write an equation here. So x squared plus y squared equals z squared. Now, it's important never to plug any of these numbers in ever unless they are not changing. Well, the y is changing, the x is changing, the distance between them is changing, the police car's speed is changing. All of these things are changing, so you can't plug anything in until you've taken the derivative. So we're going to take the derivative with implicit differentiation, 2x, then we need a dx dt. Remember, we're taking the derivative with respect to t and not x, so 2y dy dt, all the way across, 2z dz dt. All right, now that we've taken the derivative, we're on step 4. We can plug in all of our information, and we know that we are ultimately looking for this guy right here, dx dt. All right, 2 times x. X is 0.8, so that's going to be 1.6. We don't know what dx dt is, so we'll leave that as a variable. And then 2 times y. Y is 0.6, so that's going to be 1.2. We do know dy dt is negative 60. Now, you may wonder about what this z is. Well, if you just imagine pressing this police scene on pause, when it's on pause, this is, let me see if I can write it in a different color, this is going to be 0.6, and this is going to be 0.8 at the moment that we have it paused. So when we have it on pause, we're going to do the Pythagorean theorem and figure out what, at that instant, what z is. Well, this is a 3, 4, 5 right triangle. So this is going to end up being 1. All right, you can do the Pythagorean theorem and you will get that. So we know that z is 1, so that's going to be 2. And then dz dt is going to be 20. All right, so we can say 1.6 dx dt. And we will say 60 times 1.2. That's going to be negative 72. And then this is going to be 40. And so now we can move the 72 to the other side. And that is going to end up giving us 12. So we have 1.6 dx dt is equal to 112. And then if we divide 112 by 1.6, we get 70. So we can see that dx dt is 70 miles per hour. Okay, here's a pretty simple problem here. A pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. Concentric, cone, meaning same center, circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So let's identify what we've been given. We have been given dr dt. The change in radius is 1 foot every time 1 second goes past. So that's 1. It is increasing, so we make it positive. When the radius is 4 feet, so r is 4, find the rate at which the area is changing. So we're looking for dA dt. So we know that area of a circle is pi r squared. So we take the derivative with respect to t all the way across. So dA dt is equal to 2 pi r and then times the derivative of r, which is dr dt. All right, we know that r is 4, so we plug that in. So that's going to make that 8 pi. And dr dt was given to us as 1. So the area is changing at a rate of 8 pi. And since it's area, it will be feet squared per second. Square feet per second. Example 4, you have water that is running into a conical tank. All right, so once again, please pay attention to whether water is coming in or out. If it's in, that means the volume is increasing. You need to make that rate positive. If the water is going out, then it's losing volume, so you need to make that rate negative. But here it's coming in at a rate of 9 cubic feet per minute. So already they give us dV dt. It's going to be positive 9. The tank stands point down and has a height of 10 and a base radius of 5. All right, so this radius is going to be 5, and this fully filled up all the way is going to be 10. Now, there is a special relationship with cones that remains consistent no matter how much water is in the cone. It has to do with similar triangles from geometry. The ratio between this leg of the right triangle and this leg of the right triangle will always be 5 to 10. So if this is 4, this will be 8. If this is 3, this will be 6. So what we can do is we can say radius is to height as 5 is to 10. And it works only with cones. It's a similar triangle from geometry. So you can cross multiply here and get 10r is equal to 5h. So now we can get a relationship and say r is going to be 5 over 10, so that's going to be 1/2 h. All right, so that's going to make just our life a little bit easier here. So we want to know how fast is the water level rising when the water is 6 feet deep. So we're looking for dH/dt, the water level rising when the water is 6 feet deep. So h is going to be 6 at that instant. So let's go ahead and write our equation. The volume of a cone is 1/3 pi r squared h. But we can actually get rid of our r, and we're going to say, well, r squared is going to be 1/4 h squared. So we can now say volume with respect to r, it really doesn't matter here, but 1/3 pi, with respect to h, and we're going to replace r squared with 1/4 h squared times h. So that's going to be basically, when we clean that all up, pi h cubed over 12. So let's go ahead and take the derivative on both sides with respect to t. So the derivative of v is going to be dv dt, and then the derivative here by power rule is going to be 3 pi over 12 h squared, drop the power down, and then times the derivative of h, which is going to be dH dt. All right, so this is the rate that we're looking for in this problem. So let's go ahead and fill in everything. dV dt is 9, and 3 over 12 can reduce to 1/4, so that's going to be pi over 4 times h squared. Well, h is 6, so 36. Well, why did I write 39? I don't know. Let's just put that as 36. And then dH dt is now our only unknown variable. So we have 36 over 4, which is 9. So we have 9 equals 9 pi dH dt. The 9s are going to cancel. So dH dt, let's put it up here, dH dt is going to be equal to 1 over pi feet per minute. And if you get that as a decimal, I believe it's approximately 0.32. In case you're wondering, another way that that problem could have been done is by not actually getting rid of both variables and leaving them both in there. So let's go ahead and do it a second time. 1/3 pi r squared h. Now, we know that the relationship between the radius and the height, so radius is to height as 5 is to 10. So r equals essentially 1/2 h. Now, the way it works here is that you could actually take the derivative on both sides of this equation, and you can say dr dt is equal to 1/2 dH dt. So actually, we can we can actually go ahead and do this problem. And so we'll say dv dt. Now we would have to use the product rule here. So we'll call the first function 1/3 pi r squared, and we'll call the second function h. So we'll take the first function, 1/3 pi r squared, times the derivative of the second, which is dH dt, plus the second function h, times the derivative of the first, which is going to be 2/3 pi r dr dt. All right, so now we can plug in everything. So our dv dt was, remember, was 9. That's going to be 1/3 pi. Now you may say, well, what is r? Well, let's think about this. If the height is 6, then that means that the radius is going to be always half of that. So the radius will be 3. So 3 squared is 9. Now dh dt, all right, is simply going to be 2 times dr dt. So 2 times dr dt. Excuse me, we're going to leave dh dt in there because that's what we are looking to solve for. So dh dt, we'll leave that there. And then plus h, our h is 6. 6 times 2 is 12, over 3 is 4. So 4 pi, and then the radius, once again, was 3. And so now we have to replace dr dt with 1/2 dh dt. So 1/2 dh dt, and you can see where this is going here. Let's go ahead and clean this up. We have 9 equals 9 divided by 3. That's going to be 3 pi dh dt. And then this is going to give us 12 pi divided by 2. That's going to be 6 pi dh dt. We have like terms. 6 pi plus 3 pi is going to be 9 pi. So 9 is equal to 9 pi dh dt. The 9's cancel, divide by pi, and we get the same answer this way as we did before. Okay, here we have this final example here. A ladder 25 feet long is leaning against the wall of a house. The base of the ladder is being pulled away from the wall at a rate of 2 feet per second. So, before we even get started with this problem, let's think about what is changing in this problem and what is not. Well, as the ladder is falling down the wall, the y is changing the height. So we need a variable for that. So we're going to call that y. Well, this distance, the base is from the wall, is also changing. Okay, if you can just imagine this, the base is going to be sliding this way. So that's changing. So we need a variable for that. Now the one thing that is not changing here is the length of the ladder. The ladder is 25, so we don't need z. We can leave this as 25. We don't need to create another variable because it's not varying. It's the same length. So that is our basic setup here. Now it says the ladder is being pulled away from the wall at a rate of 2 feet per second. So that is the base of your ladder is moving along this horizontal line, so that's going to be your dx dt. And because it is an increasing situation, we're going to make it positive 2. All right, so now how fast is the top of the ladder moving? So we're looking for dy dt in this problem. That's our question mark. And so let's go ahead and do our Pythagorean theorem. X squared plus y squared equals 625, which is 25 squared. All right, let's go ahead and take the derivative all the way across. 2x dx dt plus 2y dy dt equals 0. Derivative of 625 is 0. All right, so we know dx dt is going to be 2. So that's going to be 4x. And then plus 2 times y. Now let's just see here. It says moving down the wall when its base is 7 feet. So this is when our x is 7. Now remember, if we just press pause on the DVD here, this ladder is always 25, and at that instant, and only at that instant, this is 7. So if we do the Pythagorean theorem, you'll have a calculator for these problems. You'll quickly find out that at that instant, and only at that instant, that the y is 24. It's a special right triangle, 7, 24, 25. So we can now go ahead and replace, some of these letters. We can say x is 7, so that's going to be 28, plus 2 times y, that's going to be 48, because that's 24, dy dt equals 0. So we have 48 dy dt equals negative 28, and we're going to divide by 48. So that's going to be negative 28 over 48, which I can divide them both by at least 4. Let's see here. It's going to be 7 over 12. So negative 7 over 12. Makes sense that it's negative because it is decreasing. And let's put some units on there. Feet per second. Okay, now this is a great problem because now we are going to be dealing with area. Consider the triangle formed by the side of the house. All right, that's that, the ladder and the ground. Find the rate at which the area of the triangle is changing at that same instant when the base of the ladder is 7 feet away from the wall. So dA dt is what we are looking for. So we're going to go ahead and write an equation for area. So the area of a triangle is going to be base, which is x, or let's just say 1/2 base, which is x, times the height, which is y. Now, once again, we don't need to write it in terms of one variable. We're going to take the derivative with respect to t, so we're going to use the product rule. So dA dt, we're going to say the first function is 1/2 x, so we'll take the first function, 1/2 x, times the derivative of the second, which is dy dt, plus the second, which is y, times the derivative of the first, which is just 1/2 dx dt. All right, let's plug everything in here. X is 7. So that's going to be 7 over 2. dy dt we found in part A, and we can use it because it's the same distance 7 feet away from the wall. So we know at that instant from part A, dy dt was negative 7 over 12. And then y we know is 24. When x is 7, y is 24. So 24 times half is going to be 12. And then dx dt is 2. So this is going to be negative 49 over 24 plus 24 over 1. And we multiply by 24 to get a common denominator. We get negative 49 plus 576 over 24. And our final answer is going to be 527 over 24. And let's see, feet squared per second. Okay, part C, we have a trig problem. We always have to put a trig problem on every application. So find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. So we're going to use one of our trig functions. So I'll say sine of theta is equal to opposite, which is x, over hypotenuse, which is 25. Now remember, we're looking for d theta dt, the change in the angle. All right, so d theta dt. So we're going to take the derivative of both sides with respect to t. So the derivative of sine of theta is cosine of theta, but times the derivative of theta d theta dt. And because theta is changing as time is changing, so we need to incorporate that. And then we have 1 over 25 dx dt. Now, you may think you need a calculator here because you may think, well, how in the world am I supposed to figure out what theta is? And then how am I supposed to find cosine of theta without a calculator? Well, remember that when we press pause on the DVD, this distance is 7, this distance is 24. We've got all three sides of our triangle. We actually never need to know what the angle theta is, but we need to know what the cosine of theta is. And we know at that instant it's going to be adjacent, 24, over the hypotenuse, 25, times d theta dt. And that's going to be 1 over 25. And then dx dt from the very beginning of the problem was 2. So we have 24 over 25 d theta dt equals 2 over 25. We multiply by the reciprocal on both sides. It's going to be 25 over 24. And that's going to cancel out the 25s. And then 2 over 12 reduces, 2 over 24 reduces to 1 over 12. And it's going to be in radians per second.